All right. We have one more section of new stuff before we do 4.6. 4.6 just puts together everything we talked about in chapter 4. We have problems that have parts A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Where's function? Look on your face, Claire. I can't take it anymore. It may say find, A part might be find where the function's increasing. B part, find where it's decreasing. C part, find relative max. D, find relative min. Find concave up, find concave down, find inflection points. And there's something else to throw into the mix now. What's this function doing as we go forever to the left or forever to the right, as x's get infinitely small or infinitely big? Those are called limits at infinity, as opposed to what we talked about, I think it was 2.3, 2.4-ish. We had infinite limits. We had when a function had a vertical asymptote, as x approaches that vertical asymptote from the left or from the right, the y's were either going to positive infinity or negative infinity. Those were infinite limits, not to be confused with limits at infinity. Limits at infinity means what's happening with the function as x gets infinitely small or infinitely big. So this page of notes, I just copied and pasted a few things from the book. Let's look at this first example. This section discusses the end behavior of a function on an infinite interval as x goes to negative infinity or positive infinity. For example, this function, as shown in this graph, you can look at an XY chart, or you can look at the graph and see that as x's get infinitely small, it appears that y's are getting close to 3. And also, as x's get infinitely big, it appears that y is approaching positive 3. So if you have this line that y's are approaching as x's go infinitely small or infinitely big, what do you call that line? It's an asymptote, and specifically it's a horizontal asymptote, as opposed to what makes the denominator 0. That's what gives you a vertical asymptote. But in section 4.5, we're talking about horizontal asymptotes. From the table or from the graph, we could say the limit as x goes to negative infinity of the function is 3. That's the limit at negative infinity. And the limit as at positive infinity means the limit as x goes to infinity of the function is also equal to 3. That means y equals 3 is a horizontal asymptote. The definition of a horizontal asymptote right there. The line y equals L is a horizontal asymptote of the graph of the function if the limit at negative infinity is L, or the limit as x goes to positive infinity is L. So you don't have to be a horizontal asymptote, you don't have to approach that number as x goes to both negative infinity and positive infinity. If there's a value L that the y's approach as x goes to either negative infinity or positive infinity, then that's a horizontal asymptote. We're going to talk about a technique used in the book for finding limits at infinity. Actually, let me go ahead and show you a couple examples in the book. This is page 236. Example 1. If I'm looking for the limit as x goes to infinity of 5 minus 2 over x squared, I know from my properties of limits that I can take limits term by term. I can take the limit as x goes to infinity of 5 and subtract from that the limit as x goes to infinity of 2 over x squared. This limit as x goes to infinity of 5 is just 5 because the function we're talking about is the horizontal line y equals 5. Y equals 5 no matter where x is going. So as in our properties of limits, we had a property that said the limit of a constant is just the constant. Not to be confused with the derivative of a constant, which is what? 0. all right? And what about this guy? If x is getting infinitely big, let's say x is 100, and then 1,000, and then 1,000,000. What's this term going to be getting close to? Yeah, you got a fraction whose numerator, it stays 2, but the denominator is getting bigger and bigger and bigger. You're dividing 2 pies up into more and more and more pieces. Everybody's getting less and less pi to the point where almost nobody has, or everybody has almost no pi. And I'm talking PIE, not PI. So the limit of that function is 5 because this guy is going to 0. This one, what about as x goes to infinity of 3 over e to the x? As x gets infinitely big, what's e to the x getting close to? E to the 100, e to the 1,000, e to the 1,000,000. What's going on there? Well, just the e part, the e to the x part, is getting huge. You raise e to the 1,000,000th, you raise 3 to the 1,000,000th power, that's enormous. So again, if your numerator is a constant, that's just a constant amount of pies that you have or cookies that you have, and you're dividing it among more and more and more and more people, the less cookies each person gets, to the point where everybody has almost no cookies. All right, so we're talking about rational functions, and we're just thinking, what's going on in the numerator, what's going on in the denominator, what's going on with the whole fraction as a result. Now, there's a technique for finding limits. I'm going to mention this technique to you, and then I'm going to tell you how I don't use it. If we were to try to find this limit by just finding the limit as x goes to infinity of the numerator and the limit as x goes to infinity of the denominator, the numerator's getting infinitely huge, the denominator's getting infinitely huge, so you end up with infinity over infinity if you try direct substitution. Infinity over infinity is something called indeterminate form. We can't say what that means. So one way to resolve that indeterminate form is what I've highlighted in yellow on page 237. When you encounter an indeterminate form, such as the one in example 2, you should divide both the numerator and the denominator by the highest power of x in the denominator. The highest power of x in the denominator is just x to the first. So if I divide all 4 of those terms by x to the first, this is what I have. And then I can see that as x goes to infinity, that would be going to 0, that would be going to 0, and all I'd have left is 2 over 1. That limit is 2. Now that technique comes in pretty handy, but I'm going to show you why I don't have to use it in just a second. Let's do it. Look at one more example of using that technique. This is example 3. If I just take the limit of the numerator and denominator separately, I'm going to have that indeterminate form problem again. I'm going to have infinity over infinity, and I can't evaluate that. But if I divide both numerator and denominator by the highest power in the denominator, that means divide all 4 terms by x squared, here's what I'll have. And this will be going to 0, that will be going to 0, that will be going to 0. So the whole thing was going to 0 over 3, the limit 0. So this technique works. In the B part, if I divide all 4 terms by x squared, then this is going to 0, that's going to 0, that would just be 2/3. And one more. Part C, if I divide all 3 terms by x squared, then that's going to 0, that's going to 0. Now I have 2x over 3. What happens to a fraction when the denominator stays the same, but the numerator is getting huge? Yeah. You got infinitely many cookies. You're just dividing by 3 people, then everybody gets a whole lot of cookies. The more cookies, the better. Yeah. All right, so that limit, and remember when you say a limit is infinity, You're not saying the limit exists. You're saying the limit doesn't exist, and here's why it doesn't exist. It doesn't exist because your y's are getting infinitely big. So this dividing technique absolutely works. I'm not arguing that. I'm arguing whether or not I actually need it. I can look in the A part and say, that's a fraction whose denominator is getting big faster than the numerator. What's going to happen to a fraction if its denominator has a higher exponent than the numerator? If the bottom's getting big faster than the top, it's going to be going to 0. I can see that. I can see that if I let me not finish that sentence. I can see if I've got a fraction where the denominator is getting big faster than the top, then the whole thing's going to 0. In the C part, I can also tell in a fraction, if the numerator is getting big faster than the denominator, the limit's not going to exist. And in the B part, I can see if x is, let's say, 1,000,000. If I squared 1,000,000 and then doubled it and added 5, the adding 5 is not going to make any difference. By the time x is huge, adding $5 to Donald Trump's money doesn't matter. All right? Adding 1 to that doesn't matter. So I would end up with like 2 trillion over 3 trillion. What's the ratio of 2 trillion over 3 trillion? 2/3. All right? So I don't actually use that dividing out technique. I just think what's going on with the numerator, what's going on with the denominator, what does that mean going on with the whole fraction? Now in this second box that I copied for you, actually, no, in the notes, the third box I copied for you says the limit of a constant divided by x to a power as x goes to infinity. That just makes sense. In a fraction, if the numerator stays constant but the denominator gets bigger and bigger and bigger, then the whole fraction's going to 0. Even the limit as x goes to negative infinity, a constant divided by negative 1 trillion is still 0. And the limit of e to the x as x goes to negative infinity, if x is going to negative infinity, if that exponent's positive, if that exponent's negative, you have 1 over e getting bigger and bigger and bigger. That's just this guy. The numerator stays 1, the denominator's getting huge, so the whole thing's going to 0. Or if you have the limit as x goes to infinity of e to the negative x, again, you got e to the negative infinity. That's 1 over e to infinity. That's 1 over something that's getting huge. The whole thing's going to 0. All right. This last box before we do some examples. This is a theorem that we used in pre-calculus, but in pre-calculus I couldn't prove where it came from because we hadn't really talked about limits yet in pre-calculus. But in the section that we covered rational functions, I gave this guideline and said if the degree of the numerator is less than the degree of the denominator is a higher power than the numerator, the whole thing's going to be going to 0. Let's get down to the third guideline. If the numerator has a higher power than the denominator, then there's not going to be a limit. The limit's going to go to either positive infinity or negative infinity. And then the second one, if the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is going to be the ratio of the two of the leading coefficients, like the 2 trillion over 3 trillion. That's just 2/3. So what I want you to do, with very little help from me, is we're going to discuss these 12 problems at the bottom of the page, and I'm going to let you try to figure out the limits and discuss it and figure it out, and then we'll talk about whether or not you're right. But even when I get into problems that have trig expressions, like example 5 in the book, think about the limit of sine as x goes to infinity. What does sine do as x gets bigger and bigger and bigger? It oscillates between -1 and +1. It's bouncing between -1 and +1 all the way to infinity. Is a limit going to exist under that circumstance? That's one of our reasons limits fail to exist if a function is oscillating between two values. So this limit is just, all you can say here is does not exist. What about this? The limit as x goes to infinity of sine x over x. I'm thinking sine of infinity, this numerator is always going to be a number between what and what? -1 and +1. What's happening to the denominator? Getting infinitely big. So I have some number, it's not always a constant, but it's always between -1 and +1, divided by something huge. What's going to be happening to that fraction? It's going to be going to 0. So I think about what the graph looks like. I think about what's happening in the numerator, what's happening in the denominator, what's happening in the whole fraction. Now, this is going to test your powers of figuring things out without a whole lot of examples. But let's work on these maybe 2 at a time. You and a buddy talk about number 20 and number 22. And then we'll see if we agree. That's a very good question. How do you write this down? Maybe that's why I'm letting y'all just talk about it, because it's hard to write anything down. I will attempt to write down something in a minute, but this is almost God whispers to you and you write down the answer. Yes, sir?
How is the answer supposed to be like worded? Do we like put the limit at x equals negative?
Either it's a number, or it's positive infinity, or it's negative infinity. Just equals.
Just equals.
Equals? Yeah, I want to know what this equals, what this limit equals. All right, let's talk about these first two. As a math teacher, it's hard for me to, I understand the meaning of an equal sign. An equal sign means this is the same as that. And that's a sacred thing to a math teacher. We don't like to misuse that. So it really bothers me to write down something in an imprecise way. I'm going to do it anyway because you need something for your notes. All right, so here's what I'm thinking about number 20. If I let x go to negative infinity, I'm going to write 5 over negative infinity, although you will never see that in a math book because it's not technically precise. And I'm going to say minus negative infinity over 3, but you will never see that in a math book because it's not technically precise. Now, what's going to become of this first fraction as the numerator stays 5 and the denominator gets infinitely small. Let's say negative a billion. 5 divided by a negative a billion is darn close to 0. So this first term is darn close to 0. That second term, you can go ahead and say minus a negative is the same as a positive. And then what's infinity divided by 3? So what's that whole expression going to be going to as x goes to negative infinity? The whole thing's going to be going to positive infinity. And when you write that, you're not saying the limit exists. You're saying, if I had 5 divided by negative a billion, that's about 0. And then minus negative a billion divided by 3, minus negative a billion is the same as positive a billion. Divided by 3 is huge. You write down infinity. You may not even have any work to show in your homework. You can write stuff like that down if it helps you, but if you can squint and figure your way through it, there's not a lot to write down on these problems. 22 is easier. What's the limit on number 22? And you use the theorem on horizontal asymptotes, or you just said the numerator and denominator have the same degree, so no matter how big or how small x is, the numerator is always going to be about 4 times as big as the denominator. After x gets down to negative a billion, adding 5 or adding 3 just becomes negligible. So that's just 4x squared over x squared. And that's just 4. All right, talk about the next two for a minute. We get to some good stuff on number 26. Yeah, 24 is so easy, just tell me the answer. Degree of the numerator is the same as the degree of the denominator. So the limit as x goes to infinity is the ratio of the leading coefficients, which reduces to a half. All right, now think about 26 and 28 for a minute. Let's go ahead and look at all 3 of those with square roots in it. 26, 28, and 30. You're going to let x be infinity on the calculator? Let's talk about 28 first. It's easiest. The limit as x gets infinitely big. Let's say x is a billion. What's the numerator going to be going to? It's getting infinitely huge. The denominator is also getting infinitely huge. So if we just tried direct substitution with something like a billion, we'd end up with indeterminate form. All right, so what's the degree of the numerator? 2. What's the degree of the denominator? You know that technically it's not true that square root of x squared plus 3 can be taken term by term. You can't just say that's the square root of x squared plus the square root of 3. That's absolutely not right. I'm not even going to write it down and have it on video. It's wrong, wrong, wrong. However, you can say that square root of 3 becomes pretty negligible as this guy gets infinitely big or infinitely small. So it is okay to say the degree of the numerator is 2, the degree of the denominator is 1. What happens when the degree of the numerator is bigger than the degree of the denominator? The top's getting big faster than the bottom. The limit doesn't exist. Y's get infinitely big when the top of the fraction is getting big faster than the bottom of the fraction. Now 26 and 28, you could think about them the same way, but you have to be careful when x is going to negative infinity. You have to remember you're putting in huge negative numbers. I don't know if huge negative means tiny or what, but hugely negative numbers. So on number 26, the degree of the numerator is what? 1. The degree of the denominator is what? 1. What does our theorem on rational, theorem on horizontal asymptotes for rational functions say if the degree of the numerator is the same as the degree of the denominator? Ratio of the leading coefficients. What would the ratio of the leading coefficients be? Well, the ratio of the leading coefficients, I just covered that up, it's 1. But what's the sign of the denominator in that fraction? Positive. The denominator is always positive because it's the square root of something. So if you put in a hugely negative number and divide it by that same positive number, what are you going to get? Negative 1. You've got like negative a billion over positive a billion. So that limit's negative 1. And what about number 30? What's the degree of the numerator? 2, and the degree of the denominator is 3. So if the denominator is getting big faster than the numerator, what's the whole fraction going to? 0. All right. Let's do 32 together, and then I'm going to turn you loose on 34 and 36. 32, the degree of the numerator is 1, and the degree of the denominator is, technically, you know you can't distribute that 1/3, but that subtracting 1 from a trillion is practically negligible, so you can go ahead and say that's basically just x squared. And so what's that limit? Yeah, the numerator is first degree, the denominator is second degree. If the denominator is getting big faster than the numerator, the whole thing's going to 0. All right, you and a buddy talk about 34 and 36 a second. What do you think the limit on number 34 is? Pi? It wouldn't make sense to say pi n because n stands for any integer, and so you're saying the limit is 1 pi and 2 pi and 3 pi and 4 pi. The limit can't be all of those different things. Either the limit exists or it doesn't exist. Maybe just pi, maybe, or does anybody have a different answer? I'm sorry, what? Does not exist. Okay, so we have a pi and we have a does not exist. Any other answers? We'll make this multiple choice and I'll vote. 0? Okay, this is multiple choice problem on a test. Pi, 0, does not exist, and anybody get a fourth choice we can throw in there? 1. Because of the Miles law of calculus. Let's think about it. As x goes to infinity, forget the cosine for a second. As x goes to infinity, what's going on with that whole fraction? Darn close to 0. So this is cosine of something that's getting darn close to 0. What's cosine of something that's darn close to 0, darn close to? You're just taking cosine of something darn close to 0 radians. You're that close to 0 radians, your y is going to be darn close to 1. And the closer the angle gets to being 0 radians, the closer the value of that whole expression will get to 1. All right, what about multiple choice possibilities for number 36? What'd you get? Okay, 1's always an option. 0's always an option. Undefined's always an option. Okay, that's your, for folks who didn't study at all and just are choosing B for everything. E? All right. Give me something else.
0.
Now I want to know what you really got. I don't believe you really got 73 pi or E out of that. What do you think the answer is? 1? We have unanimous consent on that. Anybody want to disagree? Okay. I'm thinking about it in 2 different ways. I'm thinking cosine of anything's always between 0 and, or excuse me, between -1 and +1. So at some point, this really becomes negligible when x is a billion. It really doesn't matter if you're subtracting +1 or -1 or 0 from that. So one way I'm thinking of it is that's just basically x over x, and the limit as x goes to infinity of x over x is just 1. That's one way I thought of it. Another way I thought of it was, well, I could break it into 2 fractions and say that's the limit as x goes to infinity of x over x is just 1 minus the limit as x goes to infinity of cosine x over x. This limit is 1, that limit's 0, and 1 minus 0 is 1. All right. Think about those last 3 for a second. Or a minute, a second or a minute.
That's a what I love that. Would you hear?
What do you think the answer to number 38 is?
Zero.
Zero, I got a zero. Anything else reasonable? I got a two. Positive infinity?
12.
I said reasonable. Oh, you added the 8 plus 4, so that's reasonable. Okay. Here's what I do whenever I have a negative exponent. And I may not actually be doing this on paper, but at least in my head, I'm thinking that's 8 over 4 minus, how can I write that with a positive exponent? 1 over 10 to the positive x over 2. As x gets infinitely huge, what's 10 to the x going to be doing? Yeah, and whether you divide a billion by 2 or not, it's really not going to matter. That denominator is getting huge, and 1 over huge is getting darn close to 0. So what's all that's left of that limit? But it helps me. Actually, let me say two things. If I have a negative exponent, then I realize that factor is ending up in the denominator. And if it ends up in the denominator and the numerator is a constant, that whole thing's going to 0. That would also happen if this had been 10 to the positive x over 2, but I had been going to negative infinity, then the same thing would happen. Pay attention to whether you're going to positive infinity or negative infinity. Have you had time to think about number 40 yet?
Yeah.
What do you think it is? Any disagree? Tell me how you, somebody who can explain that pretty well. Go for it, Michael.
Well, in the parentheses for the natural log,
Mhm.
x squared over x squared is just 1.
Okay,
The natural log of 1 is 0. 0 plus 5 over 2 is 5.
yeah. And it's hard to write down any middle steps for that, but basically what Michael was saying is if I split that into 2 terms, that's the limit as x goes to infinity of 5 halves plus the limit as x goes to infinity of natural log of 1. Because this stuff in parentheses is going to be going to 1 as x goes to infinity. That's going to be 1,000,001 divided by 1,000,000,000, darn close to 1. And then natural log of 1 is 0, and 5 halves plus 0 is 5 halves. All right, save the funnest for last. What about the limit as x goes to infinity of arcsecant of infinity plus 1? My brain just about gives out when I get to arcsecant and cosecant. I can think arc sine, arc cosine, arc tangent pretty well. arc secant and arc cosecant just kind of go, I miss Christina when I go, if arc secant u plus 1 is the angle whose secant is u plus 1, right? That's what this means. The angle whose secant is u plus 1. If its secant is u plus 1, then what is its cosine? 1 over, let's see, u goes to infinity of arc cosine of 1 over u plus 1. That's the angle whose cosine is 1 over u plus 1. It also helps me that that's a rational expression now, 1 over u plus 1. As u goes to infinity, what is this becoming? That's becoming 0. That's becoming closer and closer and closer and closer to 0. So this whole thing is becoming darn close to arc cosine of 0. That's the angle whose cosine is 0. Arc cosine always returns me an angle on the interval 0 to pi. In the interval 0 to pi, where is cosine 0? Pi over 2. All right, the homework for tonight is only the odd problems just like those. So 19 to 41. Starting at 63 tomorrow, we start graphing everything we know, extrema, increasing, decreasing, concavity, fractional or horizontal asymptotes, et cetera, et cetera. Yes.
Gabe,
Yes.
Gabe wants to teach this homework.
He does. Okay, let me take that from you. Thank you.
And they never